Then let's continue with the next talk by Juan Cabrera.
So, thank you very much for giving me the opportunity to present this CoRoT discovery. This is the result of the combined effort of a very fantastic team. Here you have the names of all the people who contributed to the analysis of this system that I'm trying to explain you. We managed to submit the paper 1 week ago. So maybe the referee is also among the audience. So hello, referee. I hope that you like the paper. But we are presenting a new planet. Well, we have two, but there is one that is especially interested. This is CoRoT-29. I first put the planetary parameters and the stellar parameters so you have an idea what are we going to talk about. So in principle is a regular hot Jupiter that we expect. The period is 2.8 days. You have a mass of about Jupiter mass, a radius about Jupiter radii. We have the mass from the radial velocity. Here you have the curve, it fits nicely. And we have a star which is a K0 star, okay, temperature 5200, regular star. But to draw our attention to this case, then it was not the stellar or the planetary parameters, but the shape of the transit. So this is the shape that we observe from CoRoT. And well, I don't know how much familiar, some of you are very familiar, so there's not so much, but when we see a transit, what we are sampling somehow is when the planet goes in front of the star, we sample the surface of the star behind the planet. And typically we have spherical stars with some surface brightness, and the flat part of the transit, the bottom part of the central part of the transit, is flat. So we expect something that is horizontal. And here we see something that is not horizontal. It has a significant trend. With 95 confidence level, I can say that this is a very significant trend. And this is in principle not what you expect. I mean, as you told you, when you model this transit with a standard one, you expect something flat. And the residuals that this standard model leaves, it's not acceptable. I mean, there is something that is not going well with this model. So we need an explanation of what's going on. We were thinking about different possibilities, and the best one that we could find is this gravity darkening. So when we have now, this is the same observations, I put the uncertainties of the measured data points, so you can also have an idea of which are the residuals. And this model, in yellow, so in the figure, leaves some residuals that are, this time consistent with 0. So in principle, this model can reproduce this asymmetry of the transit with an oblate star. We also, of course, to make sure that we are not making some mistake, we try to confirm this from ground. We have here the superposition from CoRoT observations. They are the gray dots. I don't know how well you see them. They are faint. And then the blue dots are observations from the Folks Telescope North, a 2-meter telescope in Hawaii. And I overplot, this is not a fit, I just overplot the model from CoRoT to the observation from ground. And we see that this asymmetry, it's not something that is intrinsic to the CoRoT data. This is something that we can confirm from ground. So the two things, the two facts, I think that this I can present here is that the transit is asymmetric, and this is not from one observation, this is confirmed from 2 different independent measurements. So which is the origin? As I told you, that we see the transit, the we sample is the star and the planet. So what if the planet is causing this asymmetry? In principle, we could assume that the planet is not spherical, it is tidally distorted, and then we can measure this tidal distortion in principle. We can go to the equations, we go to this quadrupolar moment, and it depends on the log number and the 2 terms. One, it depends on the rotation of the planet, and one on the tidal interaction between the planet and the star, which depends on the radius of the planet, the semi-major axis, and the relative masses. So this is quite standard theory, and when we try to put this model into the data, then we see that we do not arrive to explain this like. We do not have simply enough mass from the star, or if the planet is not close enough, or it's not rotating fast enough to produce this asymmetry. Moreover, we expect, the planet is tidally distorted, which can be, and some has been observed. This tidal distortion the bulge is oriented towards the star. So even if the planet was distorted, you would not see an asymmetric transit. So we discard this hypothesis as satisfactory. We can think about a disk around the star, but a disk, they should have another observational properties. We should see something in the spectrum of the star. We should see something in the reflection of the stellar light on the disk, and we don't see this. And also when the disk would be transiting in front of the star, the signature will be completely different. You can think about rings around the planet or moons, but there is no way that moons or rings at 2.5 days orbital period are stable for long periods. They should not be there. So we go through everything that we can think on the planet, and we discard by the data. So we thought about, then we have to go to the star. I mean, what is going on the star? Could the stellar spots reproduce the signal? We develop I mean, this has also been proposed for other candidates or for other planets. And then here we see a model with a spot that reproduces the data in principle and also leaves these residuals, well, something that is acceptable. Just for comparison, on the left you see the gravity darkening model, on the right you see the spot. You put the chi-square of the model, they have the same number of free parameters, and okay, the gravity darkening is a bit better, but I will not bet my career, let's say, that this is much better. But still, I mean, we don't like the spot solution. What is the reason why? I mean, the spot that we are using in this model is something like this. Here you see the stellar surface, you see the planet going in front of the star. This is the pole of the star, so this is the rotational axis of the star, and this is the kind of spot. So we have a very big spot, I mean, much bigger than the planet, because we see the spot of the planet occulting the spot all the time during the transit, and it's in a polar orbit, and okay, and it has to be stable, because as I told you, we observed this, we go in 2011, and in 2012 we observed this from Hawaii from ground, and it was the same spot, the same period, the same position. Are these kind of spots, polar spots, that can be survived for several years? I mean, actually they are. I mean, this is one example of one star. It's V410, and then you see this was observed with Doppler imaging, so this is a very bright target. We can observe really the position of the spots, and then you see that there are polar spots that can survive for longer periods. But this is a T Tauri star. This is a star that has a BSI of 75 kilometers per second. This is a completely different kind of target. I mean, we remember the star that we have here is a K0, which is slowly rotating. It's very nice. It does not show inactivity in the light curve. It does not show inactivity in the spectrum. So it's not this kind of star. We have, if we try to explain this with spots, we need to build a model which is very ad hoc. We require properties of the spots that are not observed on this kind of targets. And I mean, these polar spots are not typical of this kind of stars. So in principle, we don't like this hypothesis. Although we can reproduce the light curve, in principle, we do not believe that this is the solution. The only thing that we are left is this gravity darkening model. I don't know, well, gravity darkening, what is this? There are some stars that are rotating, for example, very fast, and they have some elongated shape. This means that when you look at the star from the Earth, you don't, at different points of the surface, you don't observe the same optical depth. Sometimes you see warmer sections of the stars, sometimes you see colder sections of the star. This means that the surface brightness is not only, well, you don't only need darkening with a geometrical effect, you also need something that tells you which is the surface temperature of the star. And this is called gravity darkening. It's well known from eclipsing binaries, and it has also been observed in the case of planets. These are some examples of rapidly rotating stars. Here you see an amplitude of some 100 of ppm in one of these. I think this is CoRoT-13. This is M dwarf. You also see that there is this asymmetry when you try these standard models. And one nice example, this is observed from ground. This is a pre-main sequence star, which is rotating again very fast, and it has a very large radius. And then you see that the planet is, well, this transit also has a very asymmetric shape because of this tidal distortion. But again, these stars here are rapidly rotating stars with very large radius. This is not the kind of star that we are observing with CoRoT. We try to do some approach. Okay, let's assume that we have a star which is not spherical. Let's describe this effective gravitational potential as the standard one, the point mass function, and then we put this quadrupole moment, which depends on the radius, and the polynomial, and then we have the rotational term. We should have added here the tidal distortion from the planet on the star, but this is so negligible in this case with the planetary parameters that we just, I mean, it didn't bring anything new to the model, so we remove it. And with this model, okay, we managed to model the star. The one thing that we get as a reward is the value of this quadrupole moment, and well, we get this value of 0.003. I don't know how familiar you are with this value for stars, but actually this is very large. I mean, it's uncomfortably large. For the Sun, it's 5 orders of magnitude smaller. And okay, we have observed some of these rapidly rotating stars, and for example, WASP 33, it has been claimed to have something 10 to the minus 4, which is still 2 orders of magnitude below what we have. So this is actually too large. There is one star that has a G2 value of 0.01. This is Archena, which is a star that is rotating so fast that it's about to be disrupted. So again, this is not the kind of star that we have here in CoRoT, where we see a baseline eye of 3 kilometers per second. No, this and a solar radius. But still, I mean, the observations are there, and we have an asymmetric transit. What is going on in this star, we cannot answer at this moment. I mean, we believe that there is something very interesting there. It has to do probably with the internal distribution of matter inside the star. But the models that we have, or the knowledge that we have nowadays on stars, are not enough to explain what is going on. There are another open questions. I mean, well, one of the advantages of this method, of this gravity darkening, it also gives us the misalignment between the orbit of the planet and the rotational axis of the star. You heard about this before. You see I took this figure from Albrecht's paper in 2012. Here you see the projected obliquity angle, and you have the effective temperature. And okay, you know, Ike and David also explained this diagram. You see the hot stars here in red, you see the cold stars here in blue. These cold stars had time, let's say the tidal interaction with the star were large, and they had time to, let's say, align their orbits, and these two outliers here, okay, call them outliers if you would like, this because they have low mass in this case, or very eccentric orbits. The tidal in time scale was not long enough to align the orbits. So they are not, in the current understanding of the theory, they are not outliers, it's just that they didn't have enough time. The position of CoRoT-29 in this diagram is here, so you also that this is misaligned. The difference with HAT-P11 and HD806 is that this one has a synchronization timescale which is 100 times lower than in the case of HAT-P11 and HD806. So this is again bringing some kind of puzzle to the game. The bad news is that, okay, we cannot really constrain the age of the system as good as we will know. So this will be the missing link to answer this question. So there are some open questions of this system. I mean, what is the origin of this asymmetry? How do we conciliate these observations? We believe that the gravity darkening is the best explanation to the light curve, although there might be another. Maybe we are missing something. We would like to know which is the age of the star, because this is a fundamental piece to study the tidal evolution of the system, and to explain this misalignment or disalignment or something. Is this something important, or it's something part of the regular evolution? And well, you notice maybe I changed also the logo. So I think this is one kind of the questions that we want to answer also with Plato in the future, when we can constrain this age parameter better. So thank you very much for your attention. I will take your questions.
Thank you. So questions to this talk here?
So just a suggestion to follow up. Sol Rappaport has published a couple of papers based upon Kepler data. So I see this planet has a 3-day period, so it's very close to its host star. And Sol found a couple of planets with very asymmetric transit profiles, much more asymmetric than you see, but his two planets were much closer in, and he is suggesting that the atmospheres around these planets are evaporating, and you're seeing something like a comet tail coming off of these planets. Maybe that's what you're seeing, but at a much smaller effect because it's further away. I see that you've got some HARPS data, and maybe if you phase the radial velocity curve with the transit, if you see a little offset, then maybe that's what this is. If you don't see an offset, then it's a red herring.
We can try to do this, thank you. I was in one of the papers which we were trying to observe this evaporation of the planets, and I always understood that the asymmetry was on the opposite direction to this that we see. But I will have to check this in detail.
Okay, another question by Tsevi Matse at the end.
I wonder, what are the error bars on those points?
Well, in this is a faint target, and in gold we only have monochromatic light curve. This will be the next step to go with.
Okay.
Just one remark, if it's a cometary tail, then the cometary tail comes first and then the planet. So, very strange. Okay.
So I understand there's some uncertainty when you try to translate the obliqueness J2 into the gravity darkening. There's some uncertainty in terms of the limb darkening law and that kind of thing. So mean, when you quote the J2 value, there must be some uncertainties, right? I mean, I just wondering how big that would be. Factor 2 also, because this.
Well, you mean this value that we get?
Thing. Okay, factor 2.
Still, I mean, okay, this is a model. In these J2s, it's a kind of phenomenological. Okay, we make the gravitational potential to follow the J2, and then we assume that the stellar surface is perpendicular to these potential solutions, and then we observe how is the transit of the planet. And then this is why we get this very big J2. I don't know if this J2 is the J2 that is telling us something about the internal structure of the star. This I cannot tell you because it will be a very strange star. But the transit is asymmetric, and if I need to make the star oblate, I need to make it very oblate.
V sin I for the star rotation is small, right?
It's 3.5 kilometers per second.
So that's slow rotation.
It's slow. Slow.
So it's slow, but you're viewing the pole of the star. So the rotation of the star actually might be, I mean, the uncertainty, yeah, it's a V sin I, right? So, but your uncertainty of, you know, how you're viewing the polar axis of the star is pretty high, and so what is the rotation? What does the physical rotation of the star need to be in order to get you a reasonable, you know, invert the question. What does the rotation of the star need to be in order to get you a reasonable gravity darkening, which then gives you a reasonable transit shape?
It's not reasonable. I mean, if you look at WASP-33, I mean, this is it's a fast rotating star, and it's still 2 orders of magnitude below. It's Arkenar. Arkenar is about being tidally distorted by its rotation. Okay. So it's still not real.
So that J2 of your 0.03 is independent of what the V sin I actually is, or what measure to be.
Well, I don't think that we can explain this by rotation. This is it cannot be. It's not the rotation. And then about the uncertainties on the rotation, I agree with you. We don't know which is the. I mean, a priori we don't know from V sin I now, but we can say this is a slow rotator. But if it was a fast rotator, at least we should see something in the Likert. This is the Likert. And this does not look like the Likert of a fast rotator. Look at, well, CoRoT32 was 0.8 days, which is also not extraordinarily fast. And you see something. You see in the activity, you see some spots, you see something in the spectrum. And here in the star, we don't see anything. The autocorrelation, I mean, it's about 40, 50, 70 days, and it's not anything like she's rotating fast.
What's the brightness of the star? How bright is it?
It's 15 magnitude.
Thanks, Tom.
Yeah, then we get to the next talk, which will be an invited talk by Kevin Heng.